Hello, everyone. My name is Amanda Haller with Audio Precision, an Axiometric Solutions brand, and today we are featuring production line tests of hearing aid devices. Today we have Director of Support and Applications, Ulla Tygard, and Regional Manager James Kelly as our presenters from Axiometric Solutions. Before we begin, I wanted to cover a few housekeeping items. A copy of today's slide deck is available through the handout section on your screen. On the last page of the slide deck, you will find additional related materials that will be covered in the webinar. If you have any questions during the webcast, you can submit them through the questions section on your screen. We will try to answer these during the webcast, but if a fuller answer is needed or we run out of time, it will be answered later via email. Without further ado, I would like to pass it over to Ulla to get us started.
Thank you, Amanda. And I will also say welcome to this webinar, production line test of hearing aids devices. We have actually divided this webinar this morning into two parts. I will take care of the first part, and my colleague James Kelly will take care of the second part. And yes, James? Here in the first part, we will actually more talk about the microphones and the couplers we are going to use for doing the test of hearing aids. But before we actually do that, then we will actually start looking at different types of hearing aids. We will also look at the standards for hearing aids, and then we will actually look at the different couplers we are using when we are talking about hearing aids. Different types of hearing aids. I'm quite sure that you are very familiar with the different types of hearing aids, but today what we actually are going to talk about is hearing aids, the hearing aids behind the ear, in the ear canal, and complete into the ear canal. Yes. If we look at a simple block diagram of an hearing aid, then it could actually look like this, where we actually have in one end the microphone, or in this industry called the transmitter. And then we have a preamplifier to amplify the microphone signal, and then we will actually go from the analog world to the digital world. So we have an A to D converter, and then we have a DSP, a digital signal processor, and it's actually here you are doing the signal processing, having higher signals at some frequencies and lower signal at other frequencies. And then we would like to go to the analog world again. So we have a D2A converter, an output amplifier for driving the speaker, or in this world, the receiver. Yeah. We can do some electrical tests. The electrical test is a test of each of these subcomponents: the A to D converter, the DSP, the D2A converter, and also the pre-amplifier and the output amplifier. We can also do a complete electrical test of the whole device for testing all the electrical parameters. Today, we are actually more talking about the acoustical test. So yeah, we got the acoustical signal, because when we are doing the acoustical test, we need a sound source in front of the microphone to generate the test signal we would like to have, and in the other end, we will mount a coupler over the receiver, so we are able to measure the output of the hearing aid. Acoustical test is a test of the complete unit. when it's leaving the production line. We also use the acoustical test for adjustment and calibration, adjustment for the patient. So we are actually adjusting the hearing aids according to the patient's hearing. Yep. Standards. When we are talking about tests, actually all types of tests, then we actually have to look at the standard for the devices we would like to test. So yeah, when we are testing hearing aids, then we do also have some standards, and the standard of interest is the IEC 60118. When we are in Europe and in Asia, the ANSI standard. When we are in the US, the ANSI standard is 322, or the ANSI standard, that's CTA 2051. All of these standards, they describe actually the parameter we are going to measure, the methods, the different tests we have to carry out, and they do also describe the tools we have to use when we are doing these tests. When we are talking about the acoustical test, then one of these standards will actually point at the IEC 60318 standard. This is a standard for all different types of couplers and ear simulators. The standards of interest when we are talking hearing aids are actually the IEC 60318-4 is the standard for the occluded ear simulator. It's also the standard called IEC 60318-5. This is the standard for a 2cc coupler, and also the new standard, the very, very new standard, is actually less than 2 months old, the IEC 60318-8. This is the standard for a 0.4 cubic centimeter coupler. We will come back to all these simulators and couplers a little bit later. So if we look at these standards, then in the general standards, IEC 60118, the ANSI standard is 22, and the CTA 2051. These standards describes the product requirement, they describe the test methods, it describes the test parameters we have to fulfill and things like that. And these standards are actually pointing at the standards for simulators and couplers, the IEC 60318, and in this case, that's 4, 5, and 8. If we look on what we are actually going to measure when a hearing aid is leaving the production line, then each of these standards, they are more or less the same. They're also a little bit different between the different standards. So in these standards, it is actually described that we have to do a frequency response. We have to do some totally harmonic distortion measurements. We have to measure noise, input. We have to do all these tests actually mentioned here. On this page, we can actually see the different chapters in the different standards where these tests are described. Most of these tests we are talking about here are actually acoustical tests. And with acoustical tests, I mean a test where we have an input signal, a sound source from a speaker, and then we will actually listen to the output of the hearing aid with an ear simulator or an ear coupler. If we look at the ear couplers available for these tests, then there are 3 main couplers, actually 4 couplers. available on the market. We have the 2cc coupler, which is in accordance to the IEC 6318-5. The internal volume of this coupler is, of course, of the words of the name, 2cc. This coupler is actually available in two versions. A version where you are using a 1/2 inch microphone, measurement microphone, or in a version where you are using a 1 inch measurement microphones. Both of these types of couplers are very, very common use on many of the hearing aids production lines all over the world. In production lines, an occluded ear simulator, according to the IEC 6318-4, can also be used. This standard also refers to the old, very well-known standard in the industry as 711 coupler. The internal volume in an occluded ear simulator is 1.26 cubic centimeter. This coupler is actually delivered with a built-in microphone. So we have a 1/2 inch microphone built into the coupler. It is actually difficult, and we will not recommend to remove this microphone for the coupler, because this microphone will, together with the rest of the mechanical parts inside the coupler, generate the right volume and generate the right resonance frequency. And then we have the third or fourth type of coupler is the 0.4 cubic centimeter coupler. It's actually also called a high frequency coupler. This coupler is in accordance to the IEC 6318-8. It is a complete new standard. It's less than 2 months old. This coupler, for this coupler, you actually have to use a 1/4 inch microphone. It's also therefore you have the possibility for measuring higher frequency, and with this coupler you are able to measure up to 16 kilohertz. Yep. See, the 2cc couplers and the 0.4 cubic centimeter couplers, as well as the occluded ear simulator, all of them need additional items before you can actually use them in your production line. The 2cc couplers, they need a microphone, and it can either be a 1/2 inch microphone or a 1 inch microphone. It depends on the type of coupler you start with. If we look at the 1/2 inch microphone, then you have two possibilities. You can either use an externally polarized microphone like the 40 AG pressure microphone, or you can use a pre-polarized microphone like the GRAS pre-polarized pressure microphone, 1/2 inch pressure microphone, 40 AO. You also need a preamplifier for the microphone, and it can either be a 1/2 inch preamplifier or a 1/4 inch preamplifier. Of course, a 1/4 inch preamplifier with an adapter. And yeah, you can either use LEMO amplifiers for the externally polarized microphones or CCP amplifiers for the pre-polarized microphones. We do also have microphone sets. A microphone set is actually a combination of the microphone and a dedicated amplifier for that microphone. So for microphone sets, we have both for externally polarized to 46 AG. We have also for pre-polarized 46 AO. And when you buy them as a set, then you will have some extra with the microphone or microphone set, as you will have TEDS data. It means there's a little chip inside the amplifier, and this chip is actually programmed with calibration data for the microphone. Microphone sets. We also have a new microphone called the 46AO. This microphone has something called SysCheck, and I will come back on the next slide on SysCheck. For the 1-inch coupler, yeah, you need a 1-inch microphone like the GRAS 40EN, and you also need an amplifier like the 26AK for a 1-inch 2cc coupler. For the occluded ear, the RA45, which actually has a built-in half-inch pressure microphone, these couplers are also available in both an externally polarized version and a pre-polarized version. And yeah, you can use the same preamplifiers, both LEMO and CCP, as you actually could use under the 2cc coupler. For the 0.4 cubic centimeter coupler, you need a 1/4-inch pressure microphone, and it's actually one of the GRAS 1/4-inch pressure microphone, either a 40 BP if it's for externally polarized, or the 40 BD or BL if we're talking pre-polarized. We can only use a 1/4-inch amplifier with these microphones. The 0.4 cubic centimeter is also available in microphone sets, actually as a complete kit called 43BB-1, 2, and 3, depending on what type of microphone, what type of sensitivity you would like to have. Yes. SysCheck microphones. What is actually SysCheck microphones? SysCheck microphone is actually a microphone with a built-in or integrated self-test functionality. It means inside the microphone we have actually added a generator or a digital to analog converter. So we actually can generate an analog signal, and we can use this analog signal as a generator and use that for checking the microphone, and not only the microphone, but also the preamplifier, the cabling, and your input of your data acquisition. If you use SysCheck, then we are actually able to detect changes in the sensitivity with an accuracy of plus minus 0.2 dB. SysCheck can also measure environmental conditions like temperature, humidity, and static pressure. So you will actually have everything in SysCheck, and you can read it out so you know the conditions on your production line when you're doing your production of hearing aids. Where to use SysCheck? SysCheck can be used in cases where it is difficult to check the entire measurement chain, where it is hard to reach the microphones. When we are talking hearing aids, then I know it's a very common procedure that you every morning will use a sound calibrator and do a calibration of your setup. It means when you are using a 2cc coupler, then you have to remove the 2cc coupler from the microphone and add and connect the microphone into the sound level calibrator and do a calibration, and then you have to mount the 2cc coupler again, and then you can start working. With the SysCheck, then you will actually be able to measure the whole measurement chains in one sequence. You actually just on your analyzer or your software press do a sys check. You can also put it in automatically, so it will do it every morning at 8 o'clock or whatever. Then it will actually do the sys check, and the outcome of this sys check will actually be that you have some LEDs on the preamplifier. There's a green LED if everything is okay, and there's a red LED if something is wrong. So an operator can be called. With SysCheck, you will actually save time in your production. You will save time for doing the disassembling and assembling and calibration. So it's easy, and you will also minimize the risk for human errors. Yes. This is actually just to tell you that if you in your production have problems on one production line with some equipment and would like to test some of the hearing aids, then the 2cc couplers are also available in a complete kit, desktop kit. So it's easy to do a verification of whatever it actually could be. This coupler kit is mainly used in R&D, but can be used in productions for doing some faster measurements if something is wrong on one production line. Yes. For the 2cc couplers, we have a lot of adapters and ear molds available for actually all types of hearing aids, BTE, IT, and in the ear canal as well. Yes. We have also, of course, for the 1-inch coupler, similar adapters available. If we look at the difference between a 1-inch microphone coupler and a 1/2-inch microphone coupler, then there are some small difference. The IEC 63118-5 is actually made according to a 1-inch microphone. The frequency range is actually described as 125 Hertz to 8 kilohertz. If we look at the standard, that is actually written in the standard. Yes, 125 to 8 kilohertz. If we have a 1/2-inch microphone, then the standard is a little bit different. It's not much. We still have a frequency range from 125 hertz to 8 kilohertz, but in the range between 6 kilohertz and 8 kilohertz, do we have a higher tolerance. So that's a little bit different in the top. And if you look at it, where we actually look at this graph here, then we can actually see the different in the high frequencies. This graph, the first graph, is actually made with the hearing aids mounted 18 millimeter from the reference plan, while the second graph is where we have measured directly on the reference plan without any modes or adapters. So you have a sound source directly on the reference plan. Yep. The 0.4 couplers is also available in a complete kit consisting of microphone and the coupler, preamplifiers, actually everything. We will come back to this slide in a while. If we compare the 2cc coupler with the 0.4 cubic centimeter coupler, then the only difference is actually the volume. It means that all the adapters, all the modes you might have already, they can actually be used together with the 0.4 cubic centimeter coupler. So it's the same adapters you're going to use. The main difference is that we have a quarter-inch pressure microphone inside, and we have a lower coupler volume. Yes, if we go to next. If we look at the main difference, then one of the difference we actually can see is that there's a gain difference between the two. The blue graph is actually the 0.4 cubic centimeter, and the green graph is the 2 cubic centimeter. So there's a gain difference, and this gain difference is actually due to the difference in volume. The major difference we actually see is at higher frequency, where the 2cc coupler has a sharp anti-resonance at about 16 kilohertz, where at 16 kilohertz we have actually a very smooth and nice level from the 0.4 cubic centimeter. So the 0.4 cubic centimeter can actually be used up to higher frequencies, and that's actually the reason why we need this type of coupler. Yes. If we look at the different high frequency coupler kits based on the IEC 380-8 standard, then we have DAS1 is externally polarized, DAS2 is a pre-polarized coupler, and DAS3 is also a pre-polarized coupler, but with a microphone, with a quarter-inch microphone with a very high sensitivity. And it means that with the 43BA DAS3, you are actually able to get almost same specification as you will have for a half-inch coupler. And in the top of that, you will have the higher frequencies, and you will also have the higher gain. So you will actually have a lot of benefits with a better signal to noise ratio. Yeah. The occluded ear simulator is also available in a kit, and normally is also used in R&D for doing some fast check, but can also be used on production lines where if you are interested in doing some tests because something aren't working correctly. Yeah. If we look at the occluded ear simulator, yep. The standard ear simulator, where we actually are using a standard half-inch microphone, has a frequency range from 100 Hertz to 10 kilohertz. It's actually the frequency range described in the standard, that it has to be like this, and there's a certain tolerance in this frequency range. With the standard ear simulator, we do also have a resonance frequency. If you look at the green curve, then you can see a huge resonance frequency, which is about 35 dB in peak. It's a halfway resonance we have in this ear simulator. If we would like to measure a higher frequency up to 20 kilohertz, then we do also have an ear simulator, again with the same half-inch microphone. The only difference is that we have damped the resonance frequency. So if you look at this 13.5 kilohertz, the peak is not that high. It's approximately 14 dB lower. and it will actually, by damping the resonance, then you will actually get a nice response, actually up to 20 kilohertz. We do also have what we call a very high frequency or high res ear stimulator, mainly made for the audio industry, so it's not for hearing aids testing. This simulator is based on a quarter-inch microphone, and therefore we are able to measure up to 50 kilohertz. Yeah. Also for the occluded ear stimulator, we do have adapters and molds for all types of hearing aids. Yes. Yes. Let's have a little overview. We start talking about the 2cc coupler. The 2cc coupler is the most common used coupler on production lines today. It has a frequency range from 100 Hertz to 8 kilohertz. In most of the production lines today, you are using a half-inch pressure microphone. But 1 inch can also be used. We do have microphone sets with SysCheck functionality available, which actually can be used for the half-inch system. We do also have the 0.4 cubic centimeter. This is the new standard released this year. Higher frequency range up to 16 kilohertz. We have the advantages of the 14 dB higher gain. And in this one, we are using a quarter-inch pressure microphone. And then we have the occluded ear stimulator with a half-inch built-in microphone. Frequency range from 100 Hertz to 10K. If we go for the high frequency version, then it's from 100 Hertz up to 20 kilohertz. And we have here a built-in half-inch microphone. I have also to mention that we have a full program of different molds and adapters for all of the couplers and simulators we see here on these slides. Okay, James, you can take over.
Okay, hi everyone. I'm going to run through slides. Let me just, and I'm going to focus on what we call TechNote 133, which is a link here to APX500 project files for a number of analyzers, specifically for hearing aid tests to meet the IEC and ANSI standards that Ola mentioned in his presentation. Just quickly refresh the fact that hearing aids are complex audio devices and usually include features such as noise reduction, have directional microphones, often include telecoils and wireless connectivity, remote controls, direct audio input, and variable programming, along with synchronization. So in order to measure these devices, we need a good quality acoustic test chamber, measurement microphone, a coupler, a sound level calibrator, or optionally SysCheck, a dummy microphone, and then an audio analyzer. But the audio analyzer should be equipped with a power amplifier to drive the loudspeaker, a power amplifier to drive the telecoil loop, a microphone power module, and a battery simulator. And the APX511 has all of those built in. So looking at the test chamber, certainly in my experience, the most popular test chamber for hearing aid measurement is the TBS25 made by Interacoustics. Extremely popular, it has excellent noise isolation, is anechoic at frequencies above 500 Hertz. An excellent response of its loudspeaker. It's very flat. A built-in loop for telecoil measurements, and has connections from interior patch panel to a rear connector panel. It makes it easy for connecting both devices and analyzers to the box. So looking at a sound level calibrator, here we've got the GRAS 42AG, has selectable frequency and SPL levels, has a built-in feedback microphone to compensate for atmospheric pressure, and can display the SPL level and frequency, temperature, barometric pressure, and relative humidity. What I would say is, if you are looking to use APX for this sort of application, if you want to include that information in your project report, then all of that could be obtained through the syscheck microphone available that Ola described. So it's monitored by the 246 AO, for example. So looking at the APX511, it's a specifically built for production test of hearing aids. And it includes a power amplifier for the loudspeaker, power amplifier for the telecoil. It has a battery simulator and CCP power for measurement microphone. Uses the same APX software as all of our analyzers, so it's a great connection between R&D and production. Very fast measurements, extremely high performance, and very flexible software. So you'll notice on the image that there's no connections on the front panel, and that's because they're on the rear panel, and we have our standard BNC input for our CCP microphone, and then we have a D-type connector which includes connections for the amplifier outputs to drive the loudspeaker, the telecoil, and it also has a battery simulator connection on there. Comes with a breakout cable to interface to the TBS25, and you can see there an image of the TBS25 rear panel. So I want to mention the APX517, and you can also use this to drive a loudspeaker using the power amplifier and obviously monitor a measurement microphone by the BNC CCP supply microphone input. You can also use the headphone amplifier to drive the telecoil. So you can do similar measurements with the telecoil output, and then an option to measure the battery current as a voltage drop across a resistor with a DC source. And the main reason I wanted to show this for hearing aids is that many hearing aids now are introducing Bluetooth as an option. So this provides a very good option at a reasonable price to add Bluetooth to a hearing aid production test line. Other modules are available, so it could also provide a reasonably priced option for R&D with perhaps a digital serial module. So you can go I2S to acoustic, for example. So now I'm going to have a look at some specific items within the project files in TechNote 133. I'm going to have a look at the measurement settings and at this point calibration. And you can see here that in the measurement sequence settings, we've got some options here. You can choose whether to continue the sequence if it fails, or in this case, it's set to cancel the sequence. Now the default is to continue. This has been changed because if you can't pass your calibration, then there's no point in continuing until you've resolved whatever issue it is that's preventing the calibration to pass. You've also got this tick box here to automatically set the generator level, which will be dependent on the configuration in here, which we'll cover in a later slide. So we have a prompt, a sequence step here, a prompt to do the calibration. Here it shows the 43AG being used, but this could also be replaced by syscheck and remove the need for that step. And you can see here as well, you can set the reference dBSPL level to the specific channel that you're using. So another thing I wanted to point out, it's not already set in the project files within TechNote 133, but if you set an expected sensitivity and tolerance, your prompt where you do the calibration will actually change color as and when it's within this tolerance, and will also cause a failure if it's outside this tolerance. So as part of the calibration, we calibrate the microphone, but we also have to calibrate the enclosure. So to make sure we're accurate when we do this, we use a dummy microphone. We use the hearing aid switched off, and then we have the measurement microphone at the reference point, and we measure a response of the chamber. So as I mentioned, acoustic output level by ticking this box here. You can see this stage set here. So when you press on this box, this is where you configure your settings for the acoustic output level. So this obviously can only be done after the microphone calibration. And this actually runs at this stage where it says measure signal path setup. So you calibrate the microphone, you set the prompt, so set everything up for the chamber, and then it will auto set the generator level. So you don't need to do this more than once, but you only do this once to set up the start and stop values to make sure you can reach 80 dB SPL in this case. So here, once we've done that, we then measure the frequency response. We export the relative level from that frequency response, and then it's imported into the next signal path, inverted. So we import that same response, inverted, as an equalization file in the signal path to equalize the chamber completely flat. Even though it has a very good flat response, it needs to be EQ'd to meet the specifications in the hearing aid measurement standards. So within the sequences, again, we have measurements and options. So on a standard measurement, we have in the measurement sequence settings, these options to continue the sequence, cancel the sequence. You can prompt the operator to retry the measurement, or you can automatically retry the measurement, and you can set a number of attempts to automatically retry, and then you can decide on failure whether to continue or cancel. So in a signal path setup for measurement sequence settings, which is this identified by this gear icon, it's slightly different. So as we saw before, you've got the auto set generator level, and if you also have this option to copy references. So in these projects, we're copying references from signal path 1, which is where we do the calibration. So it will copy the reference for the measurement microphone, and it will also copy the reference for the acoustic output level, so that you don't need to do that again. So looking at some measurement sequence steps. So many of the measurements in the projects have additional steps, and you can see this one here with a basic frequency response. We have a prompt to configure the hearing aid. We want to make a certain result visible, and this is the basic gain curve. Then we make the measurement, and then we export the result data. You could modify these project files if you needed additional steps. So you could export additional data, you could add delays, add additional prompts, ask for input from the operator, or you could import limit data, for example, etc. And there's also a run external program step here, which can be used for further automation, such as creating a command line interface executable where you pass arguments, and this could be used for communicating with the device under test, or possibly another piece of test equipment. So looking at a prompt from this project file, you can see the prompt setup dialog has a couple of tabs, general tab and appearance. And with the appearance, you can browse for an image file to include in the prompt. And then in the general tab, you can just place some text in here to instruct the operator what to do. You've also got options of which buttons to show, and there's also this preview option, and this is an image of the preview. So this is how it will be presented to the operator. So another sequence step that's used is the export results. And in this example, we're using variables to show the file location and also the file name. These are all variables defined within the They actually user-defined variables, but they're already created in this project. Also, we're adding some information into the header of this exported data, and this is the device ID, typically the serial number of the device under test. So we'll have a look at sequences. So they come with just 2 sequences, and they have a calibrate sequence and test device under test sequence. So you have options here of what to do when all the measurements pass, if a measurement fails, and you also could possibly have a password required for one of the sequences. So for example, you might want to put a password on calibrate and have this done by, say, a senior level technician. You also have this options of setting aux control, and here you could have something like a foot switch in place that runs the sequence, and it just toggles this bit high or low. You can configure this pattern to be anything you want. So we're now going to look at some pre-sequence steps and the device ID prompt. And here's an example of a prompt to enter serial number of a unit. This text can easily be changed to say scan barcode to enter the serial number, which works equally as well. So in the post-sequence steps, you can add additional steps to the pre-sequence or post-sequence steps, but comes ready with the report features. And if you look at the report properties, you have options of using our default layout. You can have a completely customized Word layout if required. You can choose to only show failed measurement results. You can choose to include the APX instrument information, which would be the serial number, calibration date, for example. You can show a measurement summary and measurement details. These are all defaults. You have another tab here, which is to automatically save the report. When you check this box, the show report will be unchecked. So typically for a production environment, you won't want to show the report every time a test is done. You can choose various formats for the report, and then you can automatically save it. You can save using a prefix. You can add a company logo using this tab. Here's an example where you might want to save it as PDF, and then hearing aid 1, and then uses the device ID variable to include the serial number. This makes it easy to find the reports. If you're searching, you can just search by serial number. If you test the device several times, it will append this with a -1, -2, etc. When you've got this, make a new file with a unique name. Another post-sequence step option is the data output option. This has very few options. You just give it a location and it will build a CSV file that includes the report date, start time, the device ID, limits, whether the sequence has passed or failed, and meter values. It will not include XY graph values. That's because this file can get very big very quickly. So within the sequences, you've also got an option of both recording and displaying variables and statistics. So you check this box and then you choose the variables and the statistics that you want to show. So in this, we're looking at the chamber ID, and this could be quite useful for seeing if there's any, let's say, problems with a specific test station, the device ID, and then we're looking at pass count and the yield, and then there's other statistics that you can choose from. Now, not only are these written to this file, this CSV file, they'll be displayed if you choose to save your project in production test mode. So by clicking this icon to lock the project, you can give it a password, you can tick the box for production test, and then you can decide whether you want to show the APX application software or not. So if this is unticked, you'll just get the prompts and results. You won't get the application window showing measurements running and graphs, etc. And then this is an example that once you've saved a project in production test mode, you'll have these two buttons to choose to either run the calibrate or test the device under test. And then dependent on what you set within the sequence settings for that project, when you, for example, when you press test device under test, it will take you through the sequence, and then at the end of it, it will come up and say next device, and you can test again and again and again, because you would probably calibrate once at the beginning of a shift and then just keep testing. So example of a production test mode running, got a list of results which will be populated with pass or fail as you run through the sequence, and very first step is to enter the device ID. So hearing aid test resources at AP, we've got the hearing aid test plugin. It's required if you want to run any of the project files in TechNote 133. It's free to download and free to use. The attack and release plugin is also required, and the Octave analysis plugin is required if you want to run the project files as is, but Octave analysis within those project files is optional. So if you were turning this into a production test sequence, you could uncheck that option within the project file. So once again, the link to TechNote 133 and project files. It doesn't just include project files for the 511 and the 517. It also includes project files for other APX analyzers used with the APX511 acoustic test interface. And then last but not least, we have a couple of videos. We have a previous webinar, a link to a previous webinar, which goes into more detail of the actual measurements within the standards, and also a link to a video on automation and production test, which again goes into more detail of automation features within APX. And we're just about on time. And I'm just looking to see if there are any other questions.
I think we have answered all questions until now. So we will stay online a couple of minutes if extra questions should come up.
Okay. And if not, Amanda can end our webinar for us.
Yes, yes, yes.
Not seeing any other questions right now. Do you think I should close it out?
I think so. There's just some
I think so.
thanks coming in, that's all.
Some thanks coming in, yes.
So, yeah.
So we will say thank you from here and thank you for participating in this webinar.
Yeah, and thank you, Ola and James, for that excellent presentation. Also, thank you to all of our attendees for the great Q&A that did come in during the webinar. An on-demand recording of this webinar will be sent out to all of the attendees by the end of the week, along with the additional handouts included in this webinar. We hope you enjoyed our presentation, and we look forward to next time.